This lecture is part of an undergraduate course on complex analysis and will be about convergence, more precisely convergence of a series. So suppose f1, f2 and so on are holomorphic on a set U. We might want to take the sum, and first we can ask if this sum converges, and then we can ask the additional question, is this holomorphic? So, for example, we might take a power series, a0 plus a1z plus a2z squared and so on, and if this converges in some open set, does it converge to a holomorphic function? Well, we've sort of implicitly assumed that it does several times, and in this lecture we will actually explain why. Another example, in the earlier lecture we had the Riemann zeta function 1 over 1 to the s plus 1 over 2 to the s and so on, which converges for the real part of s greater than 1, and we would like to know its holomorphic in this region. Slightly more complicated example is 1 over 1 to the s minus 1 over 2 to the s plus 1 over 3 to the s. And we would like to show this converges for the real part of s greater than 0 and is holomorphic in this region. Well, a series like this can be written as the limit of a sequence. So this is the limit of f1 plus f2, f1 plus f2 plus f3 and so on. So if we write these functions as g1, g2, g3, what we really want to do is to check whether the limit of a sequence of holomorphic functions is holomorphic. And there are three notions of convergence of sequences that we're going to define. The first of these says that Gn tends to Gz pointwise. This just means the limit of n tends to infinity of Gnz is equal to Gz, and this holds for all z. The second notion we're going to have is uniform convergence. We say Gn tends to G uniformly, which we will discuss, explain fairly soon. This means that somehow all the GNs, the GNs tend to G at roughly the same rate at all points. And the third notion we're going to define is that Gn tends to G uniformly on compact sets. And of these three conditions, this one here is too weak. It's not actually a terribly useful notion of convergence because it's too difficult to use, as we will see in a moment. On the other hand, this one turns out to be too strong. If Gn tends to G uniformly, we can prove lots of things about G, but the trouble is uniformly convergent sequences are fairly rare. And if you've read the story of Goldilocks and the Three Bears, you will know that this one is now going to be just right. So the definition of this is actually quite complicated and a little bit difficult to understand the first time you come across it. You may wonder why it needs to be so complicated. What I'm going to do is to show with some examples that these two conditions don't work very well, but this condition works very, very nicely. So whenever you talk about convergence of holomorphic functions, we're nearly always using this third condition. So let's start looking at these conditions. The first one is pointwise, which says that Gnz tends to Gn, tends to G of z for all z. And this doesn't work terribly well. For example, we would like the limit of Gn, if we take the limit of Gn and integrate it, we would like this to be the limit of the integrals of the Gn. And for pointwise convergence, this is false in general. There's a very simple example of this. For example, suppose we take, we could just take a unit interval, and we might take a function g1, and we might take another function g2, and we might take a third function g3 looking like this. I guess I should have put this bit in here. And you see there's a spike that's getting bigger and bigger as we approach the origin. However, you can see the limit as n tends to infinity of gnz is equal to 0 for any given z. I mean, if you pick a z here, gnz starts by getting very big, but then it sort of goes back down to 0 as n gets bigger and bigger. However, we can arrange the size of this spike such that the integral of gn is just equal to 1 for all n. So the integral of the limit is equal to 0, but the limit of the integral is equal to 1. And this is sort of really undesirable. Another example is the limit of a sequence of continuous functions need not be continuous. So here I might take g1 to look like this, and g2 might look something like this, and g3 might look something like this. And you can see the limit is going to be 0 except at the point 0 where it's 1. So the limit is of a continuous functions need not be continuous. And this is again a real nuisance. So in order to fix this, there's a notion from analysis called uniform convergence. So uniform convergence, the picture of it is something like this. So we might have a function g looking like this, and what you do is you pick a small neighbourhood of g. In other words, this is g plus epsilon, this is g minus epsilon, and for all sufficiently large functions, gn has to lie like that. So it's not allowed to have a sort of big spike sticking out. So let's contrast pointwise and uniform convergence. So pointwise, you'd say for all z, the limit as n tends to infinity of gnz minus gz is equal to 0. So on the other hand, for uniform convergence, we would say the limit as n tends to infinity of the supremum over z of gnz minus gz is equal to 0. So this is saying that the gn's must converge at each point. This is sort of saying the gn's must converge at the same rate at all points. You can try writing this out in terms of quantifiers. So for example, for pointwise, it becomes for all epsilon greater than 0, and for all z, there exists an n such that for all m greater than or equal to n, gnz, so gmz minus gz is less than epsilon. And uniform looks like this. It says for all epsilon greater than 0, there exists an n such that for all z and for all m greater than or equal to n, we have gmz minus gz is less than epsilon. So you see there's a difference that we've flipped the order of these two quantifiers. And you may have noticed that writing this in terms of quantifiers like this is extremely confusing and difficult to do, and I strongly advise you don't write out things like this because you'll probably just get it wrong. In fact, I will confess the first time I made this video, I got these quantifiers wrong. I accidentally forgot this bit here, and I'm not absolutely guaranteeing I've still got it right. So you see the difference here is that this n does not depend on z, whereas here n depends on z. So as I said, I would strongly advise not writing out long strings of quantifiers like this, because it's incredibly easy to make mistakes when you do so. Now, one of the most useful properties of uniform convergence is that the uniform limit of continuous functions is continuous. You have that in real analysis, and the proof is just the same, so I won't give it. What we're really going to use is that if Gn tends to G uniformly, then the integral of Gnz dz tends to the integral of Gz dz. This is assuming you're integrating over a finite interval. So this is a finite interval a, b. This is false if b or a is infinite. And that's very easy, because for n large, for n sufficiently large, we have Gnz minus Gn, so minus G of z, is going to be less than epsilon. So what we're going to do is to pick some epsilon, and then for n sufficiently large, this will hold. And this means that the integral of Gnz dz minus the integral of Gz dz has absolute value at most epsilon times the distance from b to a, and this tends to naught as n tends to infinity, because so this tends to 0 as n tends to infinity. Notice we need the interval b minus a to be finite. If the interval from b to a is infinite, then this fails. For instance, we can have a sequence of functions that look like this. You might take the first function to look like that, the second might look like that, the third might look like that, and they tend to 0 uniformly, but their integrals don't tend to 0. One very useful application of this is we can prove that if Gn tends to G uniformly on some region U, and Gn is holomorphic, this implies G is holomorphic. So the uniform limit of holomorphic functions is holomorphic. And the proof of this is very easy. Suppose all Gn's are holomorphic. This implies the integral over C Gn is equal to 0 by Cauchy's theorem. Here, C is going to be any finite finite loop bounding a region where G is holomorphic. This in turn implies the integral over C of G is equal to 0 by uniform convergence, because the integral of G is going to be the limit of the integral of Gn's. And this now implies G is holomorphic by Moreira's theorem. So you remember Moreira's theorem said that if all these integrals are 0, then the function is holomorphic. For example, we can apply this to the function z over 1 squared plus c squared over 2 squared plus c cubed over 3 squared, and so on, for z having absolute value less than 1, and you can easily check the convergence is actually uniform on this region, so this function is holomorphic. I should warn you that we've shown the uniform limit of analytic functions on the complex plane is holomorphic on an open region. For real analysis, the uniform limit of analytic functions need not be analytic. The problem is that if you've got any function, any continuous function whatsoever, so here's a continuous function with several spikes in, we can always find a smooth or even analytic function that's very close to it. We can just sort of smooth out all the corners. There are several ways of doing this. One of them is to take the convolution with some sort of function that's very smooth but looks like this. So taking a convolution just means we smooth out our function according to some smooth function like that. So the fact that uniform limits of analytic functions are analytic for complex variables is not at all trivial, because it's actually false for real variables. Well, so we've got uniform limits of holomorphic functions are holomorphic. Doesn't this solve our problem? Well, no, because let's look at the following example. Suppose we've got 1 plus c squared and so on, which is equal to 1 over 1 minus c for z less than 1. So here we have a sum of holomorphic functions, and it's holomorphic for z less than 1. Well, the problem is this convergence is not uniform on z less than 1. The trouble is, as z gets closer and closer to 1, the convergence gets slower and slower and sort of less and less uniform. I mean, if we look at the error, z to the n plus c to the n plus 1 plus c to the n plus 2 and so on, and we sort of want this to tend to 0. Well, this is equal to z to the n over 1 minus c. And the trouble is, as z gets closer and closer to 1, this 1 over 1 minus c sort of gets very, very big and rather messes up our estimates for uniform convergence. So we really want this error, we really want an upper bound for this not to depend on z. And this depends on z. And worse, it depends on z in a way that gets very bad as z gets close to 1. So how do we fix this? Well, suppose we just take z less than a half. Well, this error is z to the n over 1 minus c is now less than or equal to a half to the n over a half. And this now does tend to 0. And you notice this is independent of z. So we have uniform convergence on the region z less than a half. Well, we can do better than that. We can do z less than 0.9. And then we find z to the n over 1 minus c is going to be less than or equal to 0.9 to the n over 0.1. And this again tends to 0 and is independent of z. And we can do z less than 0.99. And then we get z to the n over 1 minus c is at most 0.99 to the n over 0.001, and this is, sorry, 0.01, and this is getting quite big, but it still tends to 0, and it still doesn't depend on z, which is the key point of uniform convergence. So you can see what's going on. Although it's not uniformly convergent on the whole of this region, it's uniformly convergent on a lot of approximations to it. So we want to say the limit of Gn is holomorphic. And this is a local condition. We can tell whether a function is holomorphic just by looking very, very close to one point. So we just need Gn tends to G uniformly on some neighbourhood of each point. So we don't need it to be uniform on the whole of our domain of the function. We just need it to be we just need to be uniformly locally on a neighbourhood. So you can call this local uniform convergence. And we can see that in the previous example we had local uniform convergence because although we didn't have convergence on the whole disk, we had convergence on all these smaller disks approaching it. So any point is contained in one of these orange disks on which we do have local convergence. So local uniform convergence is for at least the complex numbers, is the same as uniform convergence on compact subsets of U. And the reason for this is if we take an open set U and we take some sort of compact subset C, then what we can do at each point of C, we can find a neighbourhood such that the convergence is uniform. And since C is compact, we can cover C with a finite number of neighbourhoods on which the convergence is uniform, and it's quite easy to check that means the convergence is uniform on C. By the way, I should say the equivalence of local uniform convergence and uniform convergence on compact subsets relies on the fact that the complex numbers are locally compact. For more general topological spaces, local uniform convergence and uniform convergence on compact subsets don't have to be the same, and it turns out that local uniform convergence on compact subsets tends to be the nicer condition, so that's why people sometimes use this. So now let's have an example. Let's study convergence of power series, and what we want to do is we've got a power series a0 plus a1z plus a2z squared and so on, and let's suppose it converges for z less than r. And we want to the problem we want to solve is to show it is holomorphic for z less than r. And as we saw in some previous examples, we've got to be a bit careful because the convergence need not be uniform. So here we've got a circle of radius big R, and I'm going to take a point S here and another circle of radius R, so I'm going to take little r is less than S is less than R. So it's a little bit confusing because we need to introduce two extra numbers. And we're going to show that convergence is uniform for z having absolute value less than little r. And we're going to prove this for any little r less than big R, which will show we've got local uniform convergence. And why have we introduced S? Well, we need to for slight technical reasons. So we know an s to the n is bounded, and we know it's bounded because this series converges for z having absolute value s. So, so this number must be bounded, and this shows that an is less than or equal to m over s to the n for some fixed m. And this implies that an r to the n has absolute value at most m times r over s to the n. Now the key point is that r over s is less than 1. And this means this is a geometric series, and geometric series have really nice convergence. So for example, if we look at the error an z to the n plus an plus 1z to the n plus 1 and so on, this is going to be at most m times r over s to the n plus r over s to the n plus 1 and so on. Which is at most m times r over s to the n over 1 minus r over s. And you notice this does not depend on which value of z we choose provided, I guess I should have said z is less than r. So this does not depend on which value of z we choose, and this tends to 0 as n tends to infinity. So this is enough to give uniform convergence because we've found a bound tending to 0 that doesn't depend on z. So this shows that convergence is uniform in any open disk that's strictly smaller than the one of radius r. So this series is locally uniformly convergent, and its limit is therefore holomorphic. Now let's look at some Dirichlet series and study their convergence. So one example would be the zeta function, which is 1 over 1 to the s plus 1 over 2 to the s plus 1 over 3 to the s and so on. And it's easy to check it converges for the real part of s greater than 1. So we've got some sort of half plane, so here's real part of s being equal to 1, and it converges in this region. However, it's easy to see the convergence is not uniform. For instance, as S gets closer and closer to the number 1, the convergence of this gets slower and slower and slower. However, it's uniform in the region, the real part of S is greater than S0, where S0 is any fixed number greater than 1. So what we're doing is we're picking some number S0, and we're just looking inside this region here. And inside this orange region, the convergence is uniform. And the reason is that the sort of error term we get is going to look like something like 1 over m to the s plus 1 over m plus 1 to the s, and so on. And this is going to be at most 1 over m to the s0 plus 1 over m plus 1 to the s0, and so on. And this tends to 0 as m tends to infinity. So we get uniform convergence of the tail of the series for zeta of s, provided we stick to a region with the real part greater than s0 for some fixed s0. So the convergence is uniform in a series of regions whose union is the whole half plane of real part greater than 1. So zeta of s is holomorphic for the real part of s greater than 1, even though the convergence isn't uniform in this region. Well, now let's look at a slightly trickier example. Now let's look at 1 over 1 to the s minus 1 over 2 to the s plus 1 over 3 to the s, and so on. And the convergence of this is much less clear. It certainly converges for s greater than 0 with s real, because it's an alternating series. We want to show it converges for the real part of s greater than 0. And this is much less clear because it's no longer really an alternating series. These are going to be complex numbers with funny arguments. So we're going to show the following general result. Suppose a1 over 1 to the s plus a2 over 2 to the s, and so on, converges for s equals s0. Then it converges uniformly in the following region. And it's easiest to draw a picture of the region. What we do is we just take the point S0, and we're going to form a sort of sector. So here's the vertical line, and we have a straight line which is slightly to the right of being vertical down here and slightly to the left of being vertical down here. So we have a sort of wedge. And what we're going to do is to show that it converges uniformly in this wedge. And we can make these wedges as close as we like to the region where the real part is greater than S0. So this will implies that the function is holomorphic for the real part of S greater than the real part of S0. So it will converge in the open half plane to the right of S0 if it converges at S0. So first of all, we're going to make a simplification. We're just going to take S0 equals 0 for simplicity. And you can reduce to this case just by changing variable. So what we know is that A1 plus A2 plus A3 and so on converges. And we want to show that A1 over 1 to the s plus A2 over 2 to the s and so on converges in the following region. We take the point 0 and we take a sort of orange sector by drawing two straight lines here, and then we look inside this region here. So I want to say it converges uniformly in this orange region. So in order to do this, we need two preliminary results. This is actually quite tricky to prove, but both preliminary results are also quite useful, so I'll do them. The first is Arbel's theorem. So Arbel's theorem says what happens if you want to add up am bm plus am plus 1 bm plus 1 and so on all the way up to an bn. And there's a very nice way of rearranging this. This is equal to bm minus bm plus 1 times am plus bm plus 1 minus bm plus 2 times am plus 1 plus bm plus 2 minus bm plus 3 times am plus 1 plus am plus 2 and so on all the way up to plus bn minus 0, I guess. This is sort of bn plus 1 if you like, times am plus 1 up to an. And it's very easy to check. You can just sort of work out the right-hand side explicitly in telescopes. If you're wondering where this comes from, it's really summation by parts. So you know when you do integration, you can do integration by parts, which says the integral of ab is equal to the integral of a times the derivative of b plus various terms, that sort of endpoint terms that I'm not going to worry about. Now, integration is, of course, the analogue of summation. So here we've got a sum of ab, and we should sum over something that's a sum of a. Well, here, these bits are sort of sums of the a, so they correspond to this sum bit b. And the derivative of b, if you're doing it discretely, corresponds to a difference between two elements of b. So the terms here should be thought of as a sort of derivative of b, or a differential or difference or something. And these should be thought of as a sort of integral of the a's. And then this is a sort of analogue of integration by parts. So the next estimate we need is an estimate for the sum of 1 over m plus 1 to the s minus 1 over m to the s. And we want to estimate the absolute value of this. And I want to show it's less than or equal to 1 over m to the s minus 1 over m plus 1 to the s times s over the real part of s. So the reason for this is that this term here is going to be at most 1 over s, 1 over the absolute value of s, times the integral from m to m plus 1 of x to the minus s minus 1 dx. And similarly, this term here is going to be at most 1 over the real part of s times the integral from m to m plus 1 of x to the s minus 1 dx. Because the absolute value of this you get just by replacing s by its real part. And now you can see this integral here is going to be at most equal to this integral here, because we're just taking the absolute value of everything here, which is going to make it bigger. So this integral is at most that, and if we sort of remember we've got these, the absolute value of s and the real part of s, we have to sort of stick them in here to get an inequality between these two terms here. Now we can combine these two results to get an estimate for the tail end of a Dirichlet series. So we're looking at a1 over 1 to the s plus a2 over 2 to the s and so on. And we know that a1 plus a2 and so on converges. So what we do is we need to estimate things like am over m to the s plus am plus 1 over m plus 1 to the s and so on plus an over n to the s. So in order to prove uniform convergence, we've got to get a good estimate for this term. and we can estimate it using Arbel's theorem. So using Arbel, we need to look at am times 1 over m to the s minus 1 over m plus 1 to the s, plus am plus 1 times 1 over m plus 1 to the s minus 1 over m plus 2 to the s, plus various other terms all the way up to plus am plus an times 1 over n to the s. So we now want to estimate these, and we first of all look at all these sums here. I guess that should have been an an. So we look at all these sums here, and these are all small, say less than or equal to some fixed number epsilon, if m is large. And the reason for this is that this sum here converges, and if thus this sum here converges, then all these partial sums are going to be very small, provided m is sufficiently large depending on epsilon. So we can get a good upper bound for all these terms here. On the other hand, we can get a good upper bound for each of for the sum of all these terms, because we found an upper bound for the absolute value of this on the previous sheet, and if we add them all up, the sum of these is going to be less than or equal to s over the real part of s times 1 over m to the s in absolute value. If we combine these, we find that this sum here is going to be at most this sum here times epsilon. So everything put together is going to be at most epsilon times s over the real part of s times 1 over m to the s, and so on. And this is bounded provided s is in the funny wedge-shaped region we had before, as you can check easily. So this gives us an upper bound for this tail end term, and you can then check that this upper bound is exactly what we need in order to prove that this series is uniformly convergent on this wedge-shaped region. So this shows that Dirichlet series are uniformly convergent in wedge-shaped regions, and as we mentioned before, this shows that this is holomorphic and converges for the real part of s greater than 0. Okay, that's all I want to say about convergence.